So good morning everyone. Am I audible to you?
Good morning,
Yes, sir.
sir. Yes, you're audible.
Okay. So any before we start, any questions? Any questions so far? Any clarifications? Any queries? Okay, if there are nothing, I think we shall continue. So we are now, so we were progressively understanding what is modeling. Okay, then we understood the difficulties of dealing with ODEs. ODEs or PDEs. Then we learned transfer function. Okay, so then we have, okay, once we looked at the transfer function, we specifically look at, we started specifically looking at first and second order transfer function. This is till now we have done this much. Okay, so this is again the process dynamics part. And once we do all of this, we will go to the second aspect, which is process control. Please keep this big picture in mind. So we were, once we're done with all the dynamics, we will slowly move into the control aspects. Okay, so what have we done? So till now we have only looked at first and second order. So most of the processes that you deal with could be mostly approximated by first or second order. So what we have done is not really bad. So most of the natural systems either inherently first or second order, or you could approximate their dynamics as first or second order systems, which essentially means that this is good enough for most of the cases. But there are pathological examples wherein you will have to consider more complicated. First and second order systems are not really complicated in the sense that uh, you know how they respond to the inputs, be it sinusoidal input, be it step input, be it pulse input, so on and so forth. While first, so see, and the complexity progressively increases. First order system is the simplest. Second order system is of course slightly more complicated than first order, because then you have this notion of dampingness. So here you see the overall dynamics on mostly dependent upon only the time constant. While here it is a joint function of time constant and damping coefficient. So little bit more complicated. And most of the cases, as we really mentioned, we could be able to either the system's order would be either first or second order only, or you may be able to approximate the entire characteristic by first and second order. But so there are certain cases. Let's say if there is an exponential term in the dynamics, in the transfer function. So that is definitely not belonging to either first order, not on the second order. So how do you deal with those cases is what we are going to see. And also oftentimes we have completely ignored what is there in the, so your transfer function GFS contains a numerator, technically of course, and a denominator. All our focus till now we were mostly looking at it contains only a denominator term and numerator is most likely a constant. This may not be 100% true. So you would also have a valid numerator term. So then what is the implication? So if you have a numerator, what is going to happen? So denominator is fairly clear because that is directly connecting us to the order of the system, and if you have the first or second order dynamics till now, so we are able to understand how it is going to work. But if you have a numerator term, how that is going to affect the overall dynamics. So this is the first thing that we are going to look at it. And if there are some irrational terms, so see, first is effect of numerator. First is effect of numerator. Second is presence of irrational terms. So how do you deal with such cases? So this is the overall scheme is what we are going to take a look at now. Any questions at the moment? Any questions so far? Am I audible? Any issues?
Yes, sir, you're audible, no issues.
Okay, so now let's see how a general transfer function, how it looks like. Okay, so we will now start learning some terminologies that is really useful for us to understand some characteristic of the process. Okay, so you have a general transfer function, okay? And let's assume that it contains three different terms. One is of course S, one is a linear term in S, and third is a quadratic term in S. So which essentially means that what is the total order of the system? What is the total order of the system? Someone, please. Pardon? Pardon me.
It's order of 4.
It is essentially determined by your denominator polynomial. Okay, uh, so why? So the order, so the overall characteristics of the system is basically determined by the denominator polynomial of the transfer function. That is why the transfer function, the denominator transfer function is known as characteristic polynomial. So you also heard about characteristic function. So you heard about a term called characteristic equation. You know what is it? Do you recall? Have you heard of a term called characteristic equation anytime? Hello? Can someone comment on what is characteristic equation?
Yes, sir, we heard it in matrices. The solution
And what is that?
matrices. So
Pardon?
it is representation of a solution matrix into a polynomial.
So this is something is your characteristic equation, correct? Agreed or not?
Yes,
Tell
sir.
us.
Yes, sir.
So characteristic equation is what kind of gives rise to eigenvalues. Similarly, so this has a very one-to-one correspondence with respect to characteristic equation. Okay, so so what we are seeing G of S here is a continuous time representation of the model. So, so the most important thing is you should be able to bring out connections. Okay. So what is your G of S? G of S is basically Y of S by G of S. Output, input, which is your transfer function, whatever. A by, say, tau 1s plus 1 times S whatsoever, anything. So this, so as you really understand, they are all in continuous time. What do you mean by continuous time? So this overall system is represented in continuous time basis. What do you mean by continuous time? Can someone give a comment? Anyone, please? So forget about this. So now let's say you have a so this is continuous time or discrete time? So this is an ODE. Is this in continuous time or discrete time?
So continuous time.
And what is the discrete time equivalent of this?
So what I understand from continuous time is that a function should be defined for all time in an interval. So here we can take y as a function of t, which is
Completely agree.
continuous.
So, so precisely that is the definition. So see here, when you re-evaluate your y, correct? Y of t. So this is of course a differential equation. Your y of t would be a function, and this function would be continuous in that interval, any interval that you wanted to. So let's say you are supplying an input, your initial condition, let's say, is in the interval a and b, and you would get your y of t maybe in the interval c and d, and your function y of t will be smooth over time. It would be completely smooth. I don't know how the response looks like, but there won't be any discontinuity. It is fully continuous in time. So what is discontinuous in time? Okay, so at some point, okay, then there is some jump. You don't have. So let's say at this point, let's say this is a T naught or maybe T1. Then the next it starts from here. So there is a discontinuity here. So these are called discontinuous systems. What I am trying to say is something in between. Every continuous time systems would have its discrete time equivalent. What is discrete time? So y of t versus t, and let's say you solve this ODE. As I told, every minute point you can put. So your interval T, what are you are going to supply here, would be fully continuous, and you would get your continuous output. But when you discretize this ODE, dy by d, sometimes you may be able to get, so small cases, yes, it is possible, but most of the time your ODEs are not amenable for closed form solution. You may not be able to get yt directly as a function of something. So what in that case you do, you will discretize this. So you would put various ways. So maybe t plus 1. This is the simplest discretization, which you have already learned, I suppose, Euler's. Huh? Have you learned this in numerical methods?
Yes, sir.
So this is in continuous time. Okay, so this is its discrete time equivalent. So what are we missing here? So see, here this is discrete in the sense that anything between t and t plus 1. Huh? So it need not be t plus 1. It generally it is based on what is known as the step size. Correct? And the step size would be write in here delta h or whatsoever. So this would be generally t plus h, and the way it goes like. So what are we missing here? So between t and t plus h, you don't have output. No output because it is discrete time. While here, your ODE, when you do a closed form solution, any continuous input you supply, it would give you output. But when you do discretization, because of the approximation that you would bring in, most of the time your ODEs are difficult to solve. Then what is eventually would happen is things would be in the discrete time space, and this discrete time would lead to some what you call, you don't have a continuous output. It would be slightly between the standards. So between t and t plus h, you don't know what is your output. So instead of this continuous line, what you would get it here, it may be. So I will just draw some stars here. So you might get some points only, unlike the previous case. And you would happily join them, assuming that they would lead to your continuous time points. Is this clear? This is what you traditionally do. Any questions on this? Anyone, please?
Sir, it's clear.
Okay, so now coming to our analogy. So y of s by u of s. Okay, how are you getting y of s? And so let's say your n k by, let's say tau s plus 1. Okay, so you, what have you done? You moved from ODE space, which is continuous, and moved to Laplace space. So then your, this is, these models are continuous or discrete then? Whatever I have represented here, they are in continuous space or in the discrete space? Nothing has been lost. It is ODE was in continuous. So who told that? Discrete?
Keshav.
Okay. So why Keshav? Why do you think it is like that?
So because at some value of s, the denominator will get 0 and the whole thing will become not defined. Well, not in the
Mm,
whole interval, but there will be some finite values where we have to break the.
no, no. So I will tell you. So let's say what is our transfer function? Let's say dy by dt. Tau into dy by dt plus ky is equal to whatsoever. So I just did this transformation. I did not do anything. So whatever you see here as ODE is intact here as your Laplace transfer function. I am not talking about tau here. So if you put a different value of tau, that would have a direct impact on your ODE also. I am not doing anything of that sort. I just did a transformation and both of them are so in two different universes. One may be here, one may be here. And both of them are equally likely. I can go from here and you can come from here. Agreed?
Yes, sir.
So transfer function is a continuous time model because it is just a direct counterpart of ODE, which is also continuous in nature. Is that clear to all of you?
Yes, sir.
And the characteristics of what you call the dynamics of the transfer function would be represented by the denominator polynomial, which is called as characteristic polynomial. Agreed? Is all fine? So now
Yes.
let me do the same thing over here. Instead of this ODE, equation 1, I discretized it in the equation 1 I discretized in the times in the what you call time domain itself. Huh? Which essentially means like I just say y of t plus 1 minus y of t by delta t. Huh? Just give me. Sorry. Yeah. Let's say k times y of t, okay, plus u of t, which is equal to 0. So what are we seeing here? And I have rearranged everything. So see, eventually what are we trying to do? We are trying to develop a relation between y of s and u of s. Agreed? Or y of t and u of t. Is this clear? Is this clear to everyone? Output, sorry, input and output.
Yes, sir.
And when you rearrange so when you rearrange everything, so let's say I am going to say like this, okay? So you have terms of y of t plus 1, you have terms of y of t, you have terms of u of t. Let's say I am rearranging everything. So it is like this, y of t minus 1, I just keep on your left hand side. And let's say I couple all the coefficient of y of t and I'll write y of t. I'll couple all the coefficient of u of t and I'll write u of t. And a and b are what you call suitable coefficients, which I would kind of lump them together and write. Is that okay? Is this clear to all of you?
Yes, sir.
Is this agreed? And your so this is of course, so what you see here, this is in discrete time. And while in your continuous time, how it looks like y of s is equal to k by tau by s plus 1 is equal to u of s. So this is in, I would say, continuous time Laplace. And what is true continuous time? It is the ODE. Okay, that would be like dy by dt, tau times dy by dt, and k times maybe y plus u equal to 0. So they are all equally equivalent. This is the discrete time equivalent. This is the both are continuous. But only problem here, when you move from to the continuous time to discrete time, there would be some information loss. Why it is so? Why that is happening?
So because we are not transporting all the points.
Because of the discretization and the step size that you are seeing, you are missing this some information. So you are right. Okay, so now everything is equivalent, you see. So the denominator polynomial is characteristic polynomial. And in the continuous time, okay, if you look at the eigenvalues of A, how do you calculate eigenvalues of A minus lambda I? This is characteristic equation. While tau s plus 1 is your characteristic polynomial, everything is same. So this is in the discrete time, and this is in the continuous time. So A stands for, so when you lump everything together, the numerator effect is fully lumped in A. So the eigenvalues of A in the discrete time model is equivalent to the polynomial, the roots of the characteristic equation in the continuous time model. Are you able to correlate what I am trying to say? Hello? Are you able to correlate what I am trying to say? Any questions at the moment? So the discrete time case, so the characteristic polynomial and its roots are equivalent to the continuous time. Let's say the continuous time model, its eigenvalues, which you call them as characteristic equation. So I was trying to connect between both. So characteristic polynomial is a term that generally used in the continuous space, while characteristic equation is something that you would use it in the discrete space. Fine. Okay. With so you write with your discrete time equivalent of the model where, and when you lump all the coefficient of y. Is this all clear to you? Any questions from so far? I was trying to connect you to understand. So all these things are what I would say equally transformative. You can move from discrete time to continuous time to Laplace, Laplace to continuous time to discrete time. Everything is equivalent. Only difference between discrete time and continuous time, it would be an approximation, mild approximation, because as you would really see, there are intermediate points lost, and we are all looking at the dynamics. Any questions so far at the moment? This has to be very clear before we move ahead. Is this all clear, or any confusion, any doubts? Any questions so far? Is this clear to all of you?
Yes, sir.
Okay, so now coming back. So we just did a what you call detour, but let's come back and see what we are trying to do. Okay, so denominator of a transfer function is called characteristic polynomial, and as I told, there is an equivalent characteristic equation when you are speaking in discrete time, while the transfer function is in continuous time. Fine. So, so now let's look at the roots of these. So here s would be 0, 1 root, s is equal to minus 1 by tau. And for this quadratic polynomial, you know how to calculate. How do you calculate? Minus b plus or minus square root of b square minus 4ac by 2a. So that would result in two imaginary roots, complex conjugates that you call, and you would place them together. So your roots of a characteristic equation can be four types. So we just wrote. So it could be on your LHS of your plane, RHS of your plane, okay, and it could also occur as complex conjugates. Is this all clear? The roots could be anywhere. It can be purely on the left hand side, purely on the right hand side, and it could also be on the axis with as complex conjugate, without axis also as complex conjugate. So if there is another issue, if it could also be lie as a complex conjugate on the axis. Any questions?
No, sir.
So these positions of these roots at various locations would eventually influence your dynamics. Why? Because see, when you take the inverse, these terms, these roots is what would take kind of drive your system's characteristics. That's why we are calling what you call the denominator polynomial as characteristic equation. So when you take an inverse, Laplace inverse, L inverse, the roots of this characteristic equation would eventually, what I would say, determine how the dynamics is going to be. So what are the potential possibilities of dynamics? One, of course, you have seen very nicely converging. One additional thing that you have seen is it may be oscillatory and it converges. Fine. And there is all the more possibilities that it is never converge. It can be unbounded. These are unboundedness. So these are all bounded. What do you mean by bounded? Eventually, even though there are oscillations or whatsoever, eventually your output becomes stable. While in the other case, your output is not stable. So see, this is y of t with respect to time. So over the time increases, your output is keep on expanding. So for instance, let's say this is a temperature is what you're modeling of the temperature of a reactor. What does that eventually means? Your temperature, which is T, is increasing with respect to time. And after how long a reaction vessel would withstand temperature? Only for finite time. Then eventually this essentially indicates that a blast or an explosion. So this is an unstable characteristics of the system. While these are stable, so the oscillation is fine. Finally, it becomes converges. And one is without oscillation converges. While uh, uh, so there are some system dynamics that eventually lead to unbounded characteristics, which eventually means either a runaway, you heard of reaction runaways, and what you call temperature runaways and things like that. So if the natural system characteristic, so why are we trying to look at this? So see, things which are, so let's say this is A, and let's say this is B, and this is C. So A and B are relatively easy to control. Because eventually it is kind of controlling on its own to some extent. While C is very difficult. And what eventually you would like to, if there is such a characteristic, you should be able to define or design a controller such that this runaway or this explosion or whatever is not going to happen. So to understand whether what is the overall characteristic, you need to look at the roots of the characteristic equation. The roots of the characteristic equation would give you an idea what is the overall dynamics of the system is, and you as a designer, by looking at the position of the roots and or like the overall characteristic of the roots, you should design a controller in such a way that it's not, if it's like a what you call natural dynamics is to become unstable, you really would like to make it stable. So if you put a controller, you might want to make it like this. So this is after adding controller. Controller would try to suppress its natural instinct to go wild and try to, what I would say, give normal operation. So this would be our ultimate aim. So to understand that, so how to do this, you should know how what they call overall characteristics of the responses are, for which we are now looking at the roots of the polynomial. Is this clear to all of you now? What are we like? What is that we are going to? Any questions so far? Okay, so now, so let's look at the numerator. So till now we have not seen numerator. We were all talking great things about the denominator. What would happen? What you call if there is a numerator also contains a polynomial. Okay, so another thing is the denominator roots are called poles of a transfer function. Poles of a transfer function. If the roots of the denominator polynomial are called poles of a transfer function, in the similar fashion, the roots of the numerator polynomial, if at all it is there, it's called zeros of the transfer function. So overall dynamics is not only affected by the pole, it could also be affected by the zeros, which is the numerator roots. Okay, and eventually any transfer function, because it's in a polynomial form, you should be able to write them as a function of poles and zeros. Okay, and so in this particular example, you see that there are m zeros and n poles. And always n should be greater than n. And then only we will be able to say that the system is realizable. We'll again talk about that. So all in a physically realizable transfer function, when you model any physical system, the number of poles of the system would be greater than equal to number of zeros. So any questions at the moment? You should also try to visualize them as part of the ODE. So we never removed any characteristics of the ODE. We are just only transferred the load of the ODE to its Laplace domain. So if whatever we are trying to say, any comment that we are making, it has direct influence or the direct connection with respect to the ODE in place. Okay, so now let us look at what zeros can bring in. Okay, so now let's look at a transfer function of this particular form. So instead, in addition to the denominator roots, you will also see there is a root in the numerator. So these are the poles and these are the zeros. So your zero, you have 1 0 here and 2 poles. And what pole 0 can kind of make things do. So if your transfer function is of the form in this form 1 plus tau 3s or 1 plus tau s, this tau is greater than 0. And you, of course, there are two possibilities. Either this tau 3, which is the 0, which is the coefficient that detects the 0. It could be either greater than 0 or it could be less than 0. If it is greater than 0, what you would really see that your output would be fast enough. It would just go and eventually it will come fast. While if the coefficient that multiplies the what you call S variable is negative, what is going to happen is if your original, let's say you don't have a 0 here. Let's say your original transfer function is this particular form. It may be moving like this. But due to the presence of the 0 with the coefficient of that being negative, the dynamics would take a dip, then only it would go up. Eventually, so initially you would see that there is a dip at this point. So slope, so this is t is equal to t naught. Slope at t is equal to t naught will not be 0 and it may be negative. So if this is the positive slope, it can be a negative slope. So this is another thing that can add up if you have a numerator polynomial. If the numerator polynomial, the coefficient of the numerator polynomial will have a strong influence on the initial direction. Final direction, it doesn't have any influence. Initial direction of the response is influenced by the what you call the 0 value. Finally, your system would come back, but you would see that there is an initial dip. If there was no 0, it may have responded like this, but due to the presence of a 0 with, and not all cases, if this particular coefficient is negative, it would eventually do an initial dip, then go up. So, and this is this is of course physically you would also see when you operate system. One is so let's say when you are operating a distillation column, okay. So when you operate a distillation column and you increase or change the steam pressure to the reboiler, so you have a what you call distillation column. Okay, there is distillate going out and you have the reboiler and you suddenly change this reboiler pressure. So what would happen when you increase the pressure first, the frothing would immediately increase, okay, and as a result, so lot of spillover would happen from here to here. But this would, what would happen? So a lot of water would fall in over here. This would initially increase the boiler level. But afterwards, what would happen? Due to the increased what you call steam pressure, this would start evaporating. So even though if you look at the reboiler level here, it would initially show a dip. So rather it would initially show an increase, then it would keep on decreasing. So whatever be the case. So your first initial part of the dynamics would have a different direction compared to the final part of the dynamics. So this is basically an inverse response. So I don't know if you are trying to drive what you call uh, cars with automated manual transmission, which is called as AMT. It's not the CVT type of car, but the AMT type of car. So what in AMT you do, there would be your gears, of course, would be there, and an algorithm that is used to automate it, not really a continuous transmission. It is a manual transmission, and you made it automatic. So when you drive, okay, so let's say if you are suddenly increase the what I call speed when you are driving an AMT car, okay, so let's say you are driving at, let's say 40, and you suddenly pedaled your accelerator to make it, so to increase the speed. So you would, first observation that you would really see is a decrease in the speed. Okay, so let's say this is the speed, and based on the time that you would see, first when you put it, you would see a lag first. Then the speed would keep on increasing. This is also an example of inverse response. So initial direction should have been considering the effect. So you have pedaled your accelerator, you have pushed your accelerator, the speed should have been increased. But what it would first do is, it would just do a speed. At first, the speed would be quickly reduced, maybe for a second, then it would keep on increasing. So there are many such examples. So the first direction of the response would be very different to that of the final direction. Finally, it would catch up. So what is the problem here? So when you have this, technically your final responses might be matching, but when you take its negative turn, if the system is going to an unstable area, then that's the problem. Otherwise, you would only see it as a dip, which eventually kind of going back to its original direction. Okay, so let's consider a system, what you call, having two transfer functions parallelly, k1 by tau s plus 1 and k2 by tau s plus 1 input and output. So ys by us would be the summation of all of this. So us times, so us would be multiplied by this, us would be multiplied by this. So ys by us is equal to summation of these two transfer function. And when you take the what you call common denominator, eventually you would result in a very nice form of this particular structure. And what is that bringing? And you see, your original transfer function do not have any numerator, no numerator. Here also no numerator. So, but when they arranged them, what you call parallelly, you would see that there is a numerator transfer function, which was not there individually. So your individual, let's say this is transfer function 1, this is transfer function 2. Here there is no numerator transfer function. But you kind of arrange them in such a way that when you calculate the overall dynamics, because you know how, if there are two transfer functions, how do you calculate the overall transfer function? Because this into this plus this into this plus this. So if you take ys by us would be of this particular form. So what you would see that there is an additional 0 that is comes in, which was not there earlier. Okay, and this, if this particular term that multiplies this is less than 0, it will result in an inverse response. So what I am trying to say is, if your original system does not contain any zeros, it doesn't mean that your overall dynamics may have an influence of zeros. If though, so here your original what you call system 1 and system 2 contain no zeros, but when they arranged, when they kind of organized in a parallel fashion, it brought in an additional 0. This would result in an inverse response. While if you look at their individual operation, there won't be any what you call inverse response. But when they arrange them parallelly, y of t will definitely have an inverse response if this condition is satisfied. So inverse response, what I am trying to say is it need not be an inherent characteristic. It could also be due to an installed characteristic. There are two things connected together that could bring in their competing effects, can also bring in inverse response. Okay, so I think I'll stop here. Any questions so far? So next thing
Hello,
we
sir.
talk about, yeah.
So can we say that the zeros help us to understand the direction of the response?
It is not that it's not helps to understand. It zeros influence the direction of the response. If there are no zero in a system, you know how the system is going to work. If there is a zero, it may have an influence in the direction. Got it, no?
Yes,
Let's
sir.
say in your system there is no zero. Okay, so I'll just cut this down. So this is what a second order dynamics. Let's say it is an overdamped system. It would most likely behave like this. Fine. But due to some maybe interaction effects, it brought in a zero now. So even though your final response may be the same, but initial response took a dip, and eventually it would go like this. So the presence of the zero, but only if only if your this coefficient value is less than zero. If it is positive, there is no problem. It will be still in this direction only. So what I am trying to say is the presence of a zero can influence your initial direction of the response. As I told, this could be in a sudden change in the what they call level in a reboiler drum, when you suddenly apply a high steam pressure, or I don't know if someone of you have tried driving an cars with automated manual transmission. When you just push your accelerator, if you want to suddenly increase the speed, when you push the accelerator down, you would see a lag. The first moment the speed would go down, then only it keep on increasing. They're all corresponding to the examples of inverse response. So you will have to deal with such systems a bit more carefully. Why? Because the change in the direction. So this area, if it makes your system unstable, if it sometimes it might not make. If this area is unstable, then you have to be very, very careful. Because here you know what is happening, but the inverse direction is making things worse. You will have to deal, so you'll have to play with that system with more carefully. It might not happen, it may be just a dip, but if it goes in a wrong direction, then you'll have to deal with carefully. Is this clear?
Understood, sir.
Okay, so if there are no more queries, I think we shall stop. So we'll have our tute today. at 1 o'clock. Okay, so we'll solve the previous examples and we'll go ahead. Okay, then if there are no queries, I think we shall close the session. Bye bye. See you next week. Thank you.
Thank you, sir.